Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, good evening, good morning, good afternoon to the grade 12s. What we're going to be doing in our session today is a little bit of revision. We're going to have a look at revision under the topic of electricity and magnetism. Alright, and we're going to start with some grade 11 work, which is electrostatics. Okay, which introduces the topic of electricity and magnetism. Okay, so there are lots of components of electrostatics. Okay, starting with Coulomb's law, moving all the way to electric fields. Okay, so we're going to start off just with Coulomb's law under electrostatics. Okay, so the first thing is that we must understand about a couple of things. I'm going to run through this quite swiftly. Is the law of conservation of charge, okay, which is basically also Coulomb's law. All right. So under electrostatics, we deal with Coulomb's law, which explains a bit of charge. Okay, now there is a law of conservation of charge. Okay, that charge cannot be created or destroyed, but only be transferred by from one object to another, which leads into Coulomb's law, which is his formula. Electrostatic force is equal to Coulomb's constant, okay, and Q1, Q2 all over R squared. And we should already know the definition, so I'm not going to write it down. But Coulomb's law states that the magnitude of electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitude of those two charges and inversely proportional to the square of the distance between them. Okay, which is what we get there by the formula that we see there. Now, often when we get to an exam, we'll find that electrostatic questions are asked exactly the same way as they would be asked in our grade 11 paper. Good evening to Zuleika. I see you just popped in. How's it? It's asked exactly the same way. Okay, it's taken straight from grade 11. I wouldn't say taken straight like copy and paste, but it's the same style of question. Okay, we don't teach you anything new about electrostatics really in grade 12. Okay, but what I'm going to have a look at quickly is those multiple choice questions that can sometimes be multiple choice questions that we get when we are not given values. Okay, so let's take an example. Let's say we have 2-point charges. Okay, they're 2-point charges, or charge spheres rather. Okay, let's say we have 2 charge spheres. So let's draw them quickly. And here they are. They look more like almost looks like I was drawing stick figure people. Here we got A and here we got B. Okay. Now they're saying that there's a force of F between them. So between them here, there is a force of F. So they've given us this just a force F. We are not sure what that number is. It's just given as a variable F. Determine in terms of F the magnitude of the force between them. Okay. Now they ask us to determine what would the force be in terms of just F. All right. If the distance between their centers is halved. Okay, so now what happens if R is halved? How would we go about answering that question? Okay, first thing we need to do is understand that the force of the electrostatic force is inversely proportional to the distance squared between the centers of the 2-point charges. And we also need to understand that R in the formula here is 1 r squared. Okay, there's 1 there. There's a 1 in front here. There's a 1 in front here. There's a 1 in front here. Basic algebra, people, we cannot forget that. Okay. So also, r is now no longer 1r, but now it's half r. Whatever the value is, it's halved. Okay? Therefore, how we'd work it out for that multiple choice question is that f nu is basically going to equal 1 over a half r all squared. So in the original formula we have r squared, which is 1r squared. Now r is no longer 1r, it's half r. So everything must be squared. Alright? Which would equal to 1 over a quarter r squared. If in a different color, I can clearly see that there is a fraction that I can calculate here. 1 over 1 over 4. Alright? If I do that, I separate them. 1 over 1 over 4 times 1 over r squared. Okay? I will get 4 over r squared. So that would equal to 4 over r squared. What does this mean now? That this is equal to 4F, which means the force is going to be 4 times greater if the distance between A and B is halved. Right? Does that make sense, grade 12s? Sorry. Similarly, we can take the same sphere and we can ask a different question. Okay? Let's erase this. It is recorded. Okay, so you don't have to worry about any content lost. Okay. Now we want to find out what would be the magnitude of charge A. So let's say A is now halved. So it's QA over 2. Okay? A is now halved. Right? And R is now doubled. Okay? What is the new F? Okay? Well, first things first, we know that the formula is equal to QA, QB, all over R squared. We sub in our new values here. So, we know that's going to go to F new is going to be QA divided by 2 times QB all over 2R squared. Okay? Which, sorry, not 2R squared in brackets. Okay? Which is going to equal, of course, I've got QA over 2 is the same as a half over 4 times QA QB all over R squared. Okay? I separated the fractions over each other. Okay? So if I do that, I'll find out that a half divided by 4 is going to give me an eighth. Okay? So if I just bring this arrow over there, it's going to give me 1 over 8F. Alright? The new force is going to give me 1 over 8F. What that means is that if I have a fraction now, an inverse, okay, in the previous question I had 4F, in other words I had 4 over 1. That's a whole number. That means it's going to be greater. If I see a fraction like I see here, which is 1 over 8, which is an eighth of F, it means it's going to be now 8 times smaller and not bigger, because it's in a fraction, an inverse fraction. Alright, so what we got here, ladies and gentlemen, is the Province of Eastern Cape Education Department, and they have a grade 12 preparatory exam, a mock exam that was set. And what we're going to do is we're just going to have a quick squizzy. And let's see the multiple choice question first, if we can find any type of question. And we find one immediately here. This one is under the topic of electric field, which comes a little bit after Coulomb's law. Okay, so what I'm going to do is I'm going to wait for this question. First explain electric fields again as revision, and then we'll come back to have a look at how we can solve this question. Let me just see if there's a different one in here. This one is one as well. This is of for Newton's law question for acceleration. Okay, we can maybe give that a look at as well, maybe if we have some time. But let's go to the Coulomb's law question. We should be around about here, I think. Okay. So with grade 12, sometimes they don't ask the Coulomb's law. As you can see here, they have not asked Coulomb's law, but rather they have gone on to asking you straight to electric field strength, which is perfectly fine. Absolutely nothing wrong with this. Okay, so maybe that's what we'll just do first before we get to this question. We might just explain electrostatics full first, and then we'll continue. Okay, that's the problem with some of the grade 12 papers. They don't always have Coulomb's law in all the time. Electrostatics also encompasses the another topic of electric field strength. Okay, and we should remember from grade 11 how to draw electric field. Surely when like charges come into contact with each other, when unlike charges also come into each other, and we all should remember how to draw field lines around a point charge. But the first formula for electric field strength is defined as the electric field at a certain point is equal to the force divided by the charge at that point, okay, which is the strength of an electric field, where F is the electrostatic force, Q is the charge experiencing the force, and E is the electric field strength. What would E be measured in? Okay, its unit. It's equal to newtons per coulomb. Force is measured in newtons, and charge is measured in coulombs. Okay. We do get, obviously, another definition: at electric field strength at a point. Alright, is the electric force per unit charge placed at that point, which is another definition. Then we get electric field strength at a distance r, okay, which is E is equal to Coulomb's constant times that charge, alright, that creates the electric field, all over the distance squared. Now this formula is a little different. This is if a point charge is placed a certain distance away from a charged object. Okay, it's placed at a certain distance. Hence we get the formula K is equal to E is equal to KQ divided by R squared. Okay. Then of course they might put two charges in a field and put a point maybe in the middle of it, where it is a certain distance from both, and then they might ask you to calculate the net electric field. So net electric field would obviously be the sum of E1 plus E2, or electric point or electric field strength at A plus electric field strength at point B, etc., etc. Okay, so these are all the three formulae that exist in electrostatics that we learned in grade 11, and we take all the way through to grade 12, which is where we are now. Okay, having this formula and everything under our belts now, let's go and attempt that question 7, and let's see how well we do. Okay, so I'm going to put it up quickly. This question says a small charged sphere X carrying a charge of positive 2 times 10 to the negative 6 coulombs is placed in a vacuum. When another small sphere Y of mass 5 milligrams, which is 5 divided by 1,000 grams, carrying a negative charge is placed at point P. It accelerates from rest to a velocity of 6,25 times 10 to the power of 3 meters per second, just before sphere Y touches sphere X. The time taken for sphere Y to reach sphere X is 2 times 10 to the negative 3 seconds. First question is calculate the number of electrons that were removed from sphere X to obtain charge on the sphere. So I do believe they say that they touch each other. Draw a electric field pattern around the charges while sphere Y is still at point P. 7.3.1, calculate the net electric field strength at point P due to the charge sphere X. The distance between the charges before sphere Y moved. And also, let's have a look at the charge on sphere Y. They want you to therefore calculate. Okay, so I'm going to give you 20 minutes for this question, and I'm going to mark it with intense detail afterwards. And let's see how well we do. Let's see what we can. Let's see what we remember. Let's see what this is revision. So let's see how well we do. 7.1 says calculate the number of electrons that were removed from sphere X to obtain a charge on the sphere. Okay, so remember, you've got a positive here. So I'm just going to go over. So what we're going to do is, there's a formula I think that we learned in grade, wow, my pen's writing funny, in grade 10, I think. N is equal to Q divided by QE. Q would be the charge on the spheres or on the objects after they've touched. QE would be the charge on an electron. Okay. Now, because it's a positive charge, we're going to use the charge on a proton. Okay, so we're going to say 2 times 10 to the negative 6 all over 1,6 times 10 to the negative 19. Okay, and therefore N is going to equal 1,25 times 10 to the power of 13. It's just a number. So in other words, that's the amount of electrons that were transferred. Okay, it's quite basic. All right. 7.2 asks us to draw the electric field pattern around the charges while sphere Y is still at point P. So we can see that one is positive, okay, and one is negative. Okay, so what's going to happen is that in between them, the field lines are going to be like this. Okay, see, let me see how many I can fit in here. Okay, so that's going to be 1, 2, 3. Okay, and then they go from negative to positive. So 1, 2, straight line 1, and I'm going to make another one in here. 3. And okay, cool. I'm going to make my arrows a little different color. Okay, and in the middle here, they're going to be like this. Okay, and then the positive charge, alright, it's going to go out like this. Make this a little longer. Straight line 1. Here we go. Okay, obviously y'all guys' ones will be look way neater than mine at the moment. Okay. Okay, cool. So of course, on the outside, charge is going into different directions here, and then in the middle, of course, shows the attraction part. Okay, in other words, the positive is being attracted to the negative. Okay, and that was the electric field. Alright, I'm going to halve this, the electric field drawing. I'm going to halve this page up so we can fit 7.3 in here for some space purposes. Okay, there we go, 7.3. Alrighty, let's see. 7.3 asked calculate the net electric field strength at P due to the charge sphere X. Okay, now some information that they gave us here, they gave us a velocity. Okay, it says that when another small charge sphere or small sphere Y of mass 5 milligrams carrying a negative charge is placed at point P, it accelerates from rest to a velocity 6.25 times 10 to the 3 meters per second. So we're going to have to find out an acceleration value here. So we're going to use the formula Vf is equal to Vi. Let me see. Let me see, did they give us any time? Yes, they gave us a time there of 2 times 10 to the negative 3. So we can say Vi plus a delta t. So it accelerated from rest, so Vi is going to be 0. It's going to be 6.25 times 10 to the power of 3 plus 2 times 10 to the negative 3 seconds, and a is unknown. Okay, if we solve for that, we'll get that the acceleration, which is going to be 6.25 times 10 to the 3 divided by 2 times 10 to the negative 3, we should get an answer of about 3.125 times 10 to the 6 meters per second all squared. Okay, now we're going to need to find out what was the net force with this acceleration. So we bring in Newton's second law. F net is equal to mass times acceleration. Okay, so we take 5 milligrams, 5 divided by 1000. Or am I missing something here? It's milligrams. Milli is 1000, so 5 milligrams. Let me see. Yeah, that should be 5 times 10 to the negative 3, 5 divided by 1000. Okay, cool. So F net is equal to 5 times 10 to the negative 3. That's 5 times 10 to the negative 3 grams, 1000 grams in one. So there's 1000 milligrams in 1 gram. 1,000 grams in 1 kilogram, so that's 5 times 10 to the negative 6. Sorry, not negative 3. I apologize for that. 5 times 10 to the negative 6 is the mass, times the acceleration, which is 3.125 times 10 to the power of 6. If we do that, we'll get the net force, therefore, to equal 15.625 newtons. Okay, and now we want to find out the actual question, which says the net electric field. We can calculate the net electric field if we're working with the net force in the formula. E is equal to F net divided by Q. This now just becomes E net because we're using F net, okay, which is going to obviously equal the net force of 15.625 all divided by Q, which in this case is 2 times 10 to the negative 6, and we'll get E net therefore to equal 7.81 times 10 to the power of 6 newtons per coulomb. 7.3.2, calculate the distance between the charges before sphere Y moved. Okay, so now what we do is we use the formula E is equal to K Q over R squared. Alright, KQ over R squared. Alright, so now what do? Is we say, well, the net electric field was equal to 7.81 times 10 to the power of 6 is equal to Coulomb's constant of 9 times 10 to the 9 times the charge on sphere X, which is 2 times 10 to the negative 6, all divided by R squared, which we are uncertain of. Okay, and basically we rearrange the formula, and I'm just going to enter this on my calculator quickly. 9 times 10 to the 9 times 2 times 10 to the negative 6, all over the net electric field of 7,81 times 10 to the power of 6. Okay, let me see, what have I done wrong here? My calculator, I put the bracket on top by the exponent. There we go. Okay, we get a big number. R squared is going to equal to 2,304 times 10 to the negative 3. Well, it's not really a big number, sorry. And we're going to square root this, and therefore the distance R between them is going to equal about, I have to put this in scientific notation, 4,80 times 10 to the negative 2 meters for 3 marks. Alright, for 3 marks. Alright, that was the distance between them for 3.2. Let me see if I can half this again, and let's do 7.3.3, which was the last one there. Let's go have a look at it. The charge on sphere Y. Now, this is fairly, you can use 2 different options for this. Okay. We got our distance already, so now we're going to use, sorry, not 2 different options, we could just use this, it's only one option. The electrostatic force is equal to K, Q1, Q2, all over R squared. Okay, we've got our R already, so we're just going to square that again. We got our the net force, which is 15,625, which we calculated earlier, is equal to 9 times 10 to the 9 times Y, so I'm just going to leave that as QY, and then multiplied by QX, which is 2 times 10 to the negative 6. Was it microcoulombs, or was it just coulombs? And then we're going to divide that by 4,8 times 10 to the negative 2, all squared. Okay, and if we rearrange this formula, that's gonna this squared times that, all divided by 9 times 10 to the 9 times 2 times 10 to the negative 6. We rearrange it, therefore the charge on sphere Y, or on Q, or on Y, is going to be 2 times 10 to the negative 6 coulombs as well. Okay, but of course that'll be a negative charge, so therefore negative 2 times 10 to the negative 6 coulombs more specifically. Okay, because it's a negative charge there. Okay, that's a positive charge, so it will be negative. See, that's where the paper was. Alright guys, let's do another question from the 2013 November final matric exam. We looked at a mock exam previously, but this is a final exam, question 8 of 2013, which is my matric end of year paper that I wrote back in 2013. They give us a diagram very similar there to what we got previously, and they ask us again to draw electric field. Is it uniform or non-uniform? We can skip that question, please. Don't bother answering that question. 8.3, calculate the magnitude and direction of the electric field at point X due to a point charge A. Then they insert another point charge B. They ask is it positive or negative, and then to calculate what it is. Then question 9, nothing on there. Question 9. Okay, so we're going to do question 8 first. Okay, I'm going to see how much of 8.4 and 5 I can get in. Okay, I can get in all of it. Okay, cool. We have all the information you need there. Let's see how far we get. Alright, so draw the electric field pattern produced by point A. Alright, so with this one, we're just going to take 8 point, let me get the correct layer there. 8.1 here, 2013 paper. Just draw the point charge there, and what that'll be is an up, down, across, basically, diagonal length like that, and like a diagonal length like that, almost, but more symmetrical, of course, with just arrows going out. Okay, so I'm not going to color them all in. That'll take too much time. That's it. Okay, again, back to the question to understand it. Draw the electric field pattern produced by point charge A. So just the field pattern around A. They give us that point A has a charge of positive 16 microcoulombs. X is at a point of 12 centimeters away from point charge A. I said we're going to skip 8.2. We're going to go straight to 8.3. Okay, 8.3 means calculate the magnitude and direction of the electric field at X due to point charge A. Okay, what we do is we say that E is equal to KQ over R squared, which is equal to 9 times 10 to the 9, just maybe use some brackets, times 16 times 10 to the negative 6, 16 microcoulombs, 16 times 10 to the negative 6 coulombs, 12 centimeters, we need to convert to meters, so that's 0.12 squared. Okay, 0.12 meters. Therefore, E is going to equal 1 times 10 to the 7 newtons per coulomb. Right? That's going to be east. Okay, we add a direction on there. Cool. Then let's say another point charge B is now placed at a distance of 35 centimeters from point charge A, as shown. The net electric field at point X due to A and B is 1 times 10 to the 7 newtons per coulomb west, whereas the previous question we calculated it to be east. So therefore, with this west over here, that should give us the answer to 8.4. Is point charge B positive or negative? Alright guys, is it positive or negative? Now that you know that the direction is west, is it positive or negative? Anybody help me? Positive, is point charge B positive or negative? Alright, let me see. Why do you say it's positive, Zuleika? So the net electric field at point A was 1 times 10 to the negative 7, and that was going east, and we can see east on that compass direction looks like that's in the positive direction because east is forward, and we always take it to be positive. But notice that it says here the net electric field at point X over here due to point charges A and B is 1 times 10 to the 7 newtons per coulomb west. West is opposite to our direction east. So now based on that direction, is point B positive or is it negative? Zuleika, do you stick with your answer? She does. I see. She's also right. Okay, cool. The thing is, with a lot of students, we like to sometimes second guess or doubt ourselves. Okay, point charge B is indeed positive. Okay, is point charge B positive or negative? It definitely is positive. Okay, so 8.4, the answer to that is positive. Okay, the last question just before we say goodnight, according to the time that we got here, 8.5. 8.5 says calculate the magnitude of point charge B now. Okay, let's see how we did this one. Okay, so we now know that the electric field at point, let's see, at point A, the net electric field at point A plus the electric field at point B must equal the net electric field value. So the net electric field at point A was 1 times 10, or the electric field at point A was 1 times 10 to the 7. We don't know what is the net electric field at point B, but that equals to minus 1 times 10 to the negative, or 1 times 10 to the 7. This minus over here indicates the westerly direction. right? Just so that you know. Because our answer for electric field at point A was 1 times 10 to the 7 east. Okay? Just so we know. Cool. Now that we have that, this comes over, and we find that therefore the net electric, or the electric field, at point B, that becomes a minus, is minus 2 times 10 to the 7 newtons per coulomb, which is just equal to 2 times 10 to the 7 newtons per coulomb, and that's also going to go in the westerly direction. Okay, we just leave it at that. Now we substitute it into the formula. E, electric field at B, is going to equal KQB, the charge on B, over R squared. Okay, we know this value, we just calculated there, so it's 2 times 10 to the 7, we don't include the negative, 9 times 10 to the 9, QB is unknown, all over. Now watch this. B is 35 centimeters away from point A, so and A is 12 centimeters from point X, so B would be 35 minus 12 from point X, which gives us to 23 centimeters, so that's 0.23 meters. We're going to square that, and this is going to be multiplied by that and divided by that. Therefore, QB is going to equal 1,18 times 10 to the negative 4 coulombs. And grade 12s, that's it for our revision session for this week. Thank you so much for joining, and we will revise a new topic next week.